This is last of the 3 videos of the assignment 4. All these videos are based on my experience doing the assignment. You should also take a look at the Piazza where you can find many hints on how to deal with your assignment. Once again, let's go back to the memory map of big int add. So I'm particularly interested in this function where you have 3 arguments, 7 arguments. And as we saw before, they're going to be on the stack stored like this. RSP is 1000, which is pointing to the top of the stack. So if I want to get OADD1 address, I need to add 48 to RSP to get to here. Now, suppose I want to look at the OADD1 structure on the heap. So this would take however many bytes. That's the structure for this. This is a pointer to the structure. So OADD1 must contain, let's say, for example, the address 100, which is the address of the first byte that gives you the heap memory for this stack, this structure. So the first one is the L length, and the second one is going to be 8 bytes from there, 16, 24, and so on. You can find the other things that are stored. If you go to the next slide, we can talk about essentially how these things can be addressed. The address of OADD1 is 1048 in this example. And then if you add RSP plus 18, where the RSP should be, in this case, the RSP should be 1000. So if you add RSP plus 48, you're going to get 1048. That's the address of OADD1. What's the content of OADD1? Now that's going to be a memory location reference. So we take 48 offset from the RSP pointer. You get that. So the content of OADD1 is 48 RSP. And now it's if you take that, that's the address of L length 1. Or L length here, which is, say, in this example, it's a 100. Now the content of that address, so if you want to get the L length, the value of L length, let's say it's a 0, I want to get that, what I need to do is to dereference that. So I take I move this into some register, say I'm going to move this into an RAX register. Okay, let's suppose that at the address of L length, which is 100, is in the RAX register right now. So what we can do is to dereference that to get the content, which is 0 in this case. So that's very important to know. Let's take a look at the next one. I'll fix this one here. In this case, we want to find the OADD1, this array element here. So again, we are going to work with the same addressing examples. So what we want to use is the operation to access this operation, the offset of the structure, the base address, index, and the size of each element. So suppose the index 2 is in R10. Size of each element is 8. And the base, which is the value of OADD1 as shown 1, let's suppose it's in array X. And the offset of AUL digits is, based on the structure, is going to be 8 bytes from the beginning of that. So that would be 8. So in order to address that element, this particular thing, you have to write this statement. Now, if you need the address of this, then you can use the LEAQ operation to get the address of this particular thing. Like, for example, I want to know what 124 is. I can do the LAQ, the content, and it'll give you the effective memory address for that. So that's an important thing. So the other thing that are important is that how do we do operations? For example, I'm going to use my example here. So for example, if you're going to compare two things, so obviously in my style of writing, I'm going to always move ULD max to some register. And then I'm going to compare with UL max. So this means this has UL new max and this has UL max. Now it's important to know that the compare Q operation always look at the second argument against the first one. So if you use the command like greater than or equal to, you're asking the question, is this greater than or equal to that? Or less than or equal to, you're asking, is this less than or equal to that? So those are the things that you have to be very careful of. Also, one other thing that's really important is how do you move some value, maybe it's in a register, into a memory location, right? Like this one here. So what you need to do is to form that memory location first. So you form the memory location that represents that, then you say move R11, and the R11 is the UL max. So I'm moving what's in the register to this memory location. We want to make that this should be a memory location, not a register. Because if you do something like move 11 R10, R11 into R10, where you had put this in R10, it's not going to change this memory location. So keep that in mind. That's very important to know. All right, next we look at the how to use GDB to inspect numbers. Another important thing in doing this assignment is using the GDB creatively to inspect things as you go through a debugging process. So there are a few things that I do that are important. I use the Emacs GDB mode. To do that, I have to create the executable with the -G flag. And then first I type Emacs, and then I press Escape X, and then I type GDB, name of the executable. And I usually set a breakpoint at 1, and then I run the code run with the arguments. Usually I advance to the next line using N, but when I see a function coming up, I'm going to use S because it's going to step into the function. So what are some of the common errors that you can run into? Some common errors are things like incorrectly referencing memory locations. So this means suppose you need to look at this element and this element here. So add in 1 and add in 2, digit 3. Suppose your code may look like this. You're going to move maybe the addend 1 into R10, addend 2 into R11. The addend 1 or addend 1 A will digits 3 into R10 and R11, right? So you're expecting these things to have some integers or some values that you can read. At this point, when you get to that place, you can register after you pass these two, you can check the registers R10 and R11. So what you need to do is to say information info register R10, info register R11. Suppose you see maybe 2 for R10, but some hexadecimal number for R11. So this means you know something has gone wrong. You're not comparing the correct things. You're expecting an integer for both, but R11 seems to refer to some address. So in that case, what I would do is to look at the code to see what the error is. The possible errors are R11 is not properly accessing the content that you want to get. Maybe the R11 is corrupted in between before you get there. So the third thing is the seg faults. Now, seg faults are often caused by illegal access of protected memory. You can type where after your program crashed to see the assembly lines that cause the seg fault. Or what I do is I patiently step through each assembly code until I find the error. When I find the error, I'm going to check if the translation from flattened to assembly is correctly done. Then I'm going to check if the memory is accessed correctly. You can look at the memory map diagram to understand that. And then when I step through this, I'm just going to use some small things like Fibonacci 2, where I can see maybe the loop runs only once and trying to add Fibonacci 0 and Fibonacci 1 to get that. So it's easy to see what's happening in the registers and how they're being compared. So once you fix the small fib, I'd say 2, it may also work for other values, since error is probably in translation from flattened to C. from Platin to assembly, actually. I should say assembly here. And or erasing some incorrect references or memory registers in how you compare and jump. You have to patiently step through these uh, uh, code with a small Fibonacci to figure. So finally, when you do the optimal, or you're trying to beat the compiler, there are three things that are really important. One is you want to look at the loop patterns described in section 3.67, make the inline calls, use the add CQ operation. Let me go over some of these things one by one. So if you're given a for loop, you can convert it to a while loop like this. It's fairly easy to see how the for loop can be done in while loops, because we prefer to write for loops, but really you should be thinking about while loops. Now, one translation of a while loop is the while test body. You do the test in the beginning. If it fails, you go to done. Otherwise, you do the body and then test it again. And this is like a do while version of the thing. And go to version would be we write something like if test go to loop. So if not test, go to done. Otherwise, go to loop. Now, one other way you could take an advantage of changing loop conditions is to do the following. We introduce something called jump to middle translation. Suppose you have a while body like this. So what we're going to do is we're going to go to the test first. So instead of testing in the beginning, because we know the beginning test may always be true, there's no reason to do the first test because most likely it's going to be true in 1 out of a million cases. So we're going to push that test to the end of the loop. And there are some very interesting advantages you will gain by doing this. You should read into that chapter to understand that. So instead of testing in the beginning, I'm going to test first at the end. So go to test in the first one, test it. If test fails, you're going to be done. If test doesn't fail, you're going to go back to loop. So essentially, this form seems to improve your performance quite a bit. So we'll take a look at that with an example. So let's take a look at how to gain an optimization advantage by moving things around. In the example that I've been showing you, I have this standard conversion of a for loop into a while loop. So I'm checking the negation of the condition in the beginning and going to the end loop when it's true. Now I'm going to rearrange that code in a different way. So this is called the go to middle technique. So I will have I index 0, and then I will go to the middle immediately. And at the middle, I'm checking the regular condition of a while loop. It says while I index is whatever, go to begin loop. So now if that condition is true, I'm going to go to begin loop. So the begin loop, this means that the begin loop will start to execute that. And note that I have removed this and I have these three statements. So I have these three statements that I want to execute. Then I have the I index. And so the only difference between this and this is that I have this strategy where I assume that the first condition always going to be true. So we're just going to keep things together here and jump to the middle to start executing the actual while condition, not the negation, and then do that. So by doing that, you can gain some advantage of the runtime. So you will see this. So what you need to do is now, just as you converted your flattened C code into assembly code, change your flattened C code to look like this, and then change it to the assembly code. You can get some advantage. So as we discussed, if you use the jump to middle technique, that you can get the same optimization as the compiler's dash big O flag. That's something you need to remember. The second optimization you want to do is the inline call the big int larger function. So how would you do that? Let me show you an example of how I did it for myself. So in this particular example, I have this find max function which goes from here, so all the way from here to here. That's the end of the find max function. Then I call the find max. Now in the new version, I removed that find max function. So find max is completely gone. I'm starting with the set max. So in the set max, in the original version, I have the call to the find max right here. Somewhere here is the call to the find max. So what I need to do is to change that call so that find max is inlined. So how do I do that? So here's how I do it. Notice that this part of the code, it's pretty much the same. I didn't really try to change anything there. And then the only thing I change is the call find max, which is given here. This is the same line find max. So I know the first argument is RDI, second is in RSI by the time you're done with these two. So I compare the two things. If it's greater than or equal to, then the second one is the max. So I'm going to put the second one in the max memory space. Otherwise, I'm going to put the first one as the max, which is in RDI, and jump to the end of max. So essentially, I removed this call find max, which means that you have to go use more registers, you have to do more work just by inlining this few lines of code here. And that's going to take care of this. So that's how you can inline the code. So finally, the add CQ operation. Now, proper use of this operation is the one that's going to get you the biggest optimization for your code. So there are two approaches. Now, typically, if you assume that you have two operands in two registers, to call them OP1 and OP2, and let's say sum is also registered. If you want to add OP1 and OP2 to the sum, what I can do is I can add OP1 to the sum, then add OP2 to that sum. So I will have sum is equal to sum plus OP1 plus OP2. Now in this case, it's possible that an overflow occurred. You have to deal with carry separately to deal with this overflow. On the other hand, if I replace that by add CQ, carry will be part of the sum. There are still many more details that I won't go into here. You can either read Piazza or lecture notes to understand how the flag system needs to be also adjusted to gain an advantage of using add CQ as opposed to add Q. So in this case, you may be able to remove the handling of the carry in your code just by using add CQ operation. And that's going to give you the best optimization possible.